Alright, what's up guys? In this video I'm going to pick up some calculus here. This is going to be another integration practice video. This is going to be example number 41 of the integration practice series. So we're asked to evaluate the integral dx over x times the square root of 16 plus x squared. Okay, so this is a good time to do a trig substitution. So let's try that. And as I mentioned in the last video, if you're still struggling with trig substitution and don't know how to do it, I have plenty of videos on it, so please check those out. I don't want to waste too much time talking about the method or the technique in this particular video, as I have other videos for that. So in this particular case, we can easily tell that this is a tangent substitution because we have the square root of, well, it looks like we have the square root of a squared plus x squared. And so remember, if we have that, then that's just x is equal to a tangent theta, which is what we do have here. So we need to identify what a is. So in our case, a is going to be 4, because if I take the square root of 16, I'll get 4. So that means that x is equal to 4 tangent theta. We need to take the derivative. That's 4 secant squared theta. Don't forget to multiply by d theta. Now we go to our integral and we plug the stuff in. So this will be 4 secant squared theta. Don't forget about the x that's right there. That's going to be 4 tangent theta. Now I got to multiply that by 16 plus 4 tangent theta squared, integrated with respect to theta. So that's basically how you set it up. Okay. So again, we'll take care of the square root stuff right now. So this will be 16 plus 16 tangent squared theta, which I can write as 4 times the square root tangent squared theta plus 1, which we know is secant squared theta. If I take the square root of secant squared theta, I'll get secant theta, so then that'll be 4 secant theta. And we take care of the square root. Now we do have a 4 tangent theta down here, so we can't forget about that part. So we didn't touch the 4 secant squared theta. We didn't touch that. And we would essentially have a 16 down here because we got 2 4s. So this would be 16. And then we'll have tangent theta, and we'll have secant theta, or times secant theta, d theta. Now we know we can simplify 4 over 16. We can also cancel out one of the secants, because there are 2 secants here, 1 down there, which means it's just going to leave us with a secant left over. 1 over 4 is a constant. Again, we can reduce 4 over 16 to 1 over 4. So I'm going to pull out 1 over 4. And then it looks like we'll just end up having secant theta over tangent theta d theta. Alright, so now we need to deal with this here. This is a perfect opportunity to probably use, this is a good opportunity to probably use a tangent, what we can do is we can use a tangent half angle substitution. It's been a while since I've actually had to use this, but I don't see any other way of dealing with this. So remember, for the tangent half angle substitution, we'll just do t is equal to tangent of theta over 2. Okay. And so if you recall learning about this, it may be a while since you've used it. So if you recall, remember that tangent of x, that's just going to be equal to 2 tangent of x over 2. And then we'll divide all of that by basically 1 minus tangent squared of x over 2. So hopefully you remember that. And also recall that secant, in our case, we'll call that secant of x. Remember, that's just 1 plus tangent squared of x over 2 all over 1 minus tangent squared of x over 2. And so what we need to do is we need to stick the following information into the integral. So once we simplify basically everything up here, we'll just get 2t divided by 1 minus t squared when we simplify that part. And for this part, we'll get 1 plus t squared all over 1 minus t squared. Okay. The only problem with well, I won't say it's a problem, but what makes it a little difficult is a lot of times we're using a tangent half angle substitution. It'll give you some nasty looking integrals that sometimes end up reducing down to some really hard partial fractions. In this case, I'm not seeing that it's going to be an issue. So I got dt. So again, remember, nothing happened to the constant 1 over 4. And so if we simplify all of this over here, we'll just be left with, looks like we'll be left with a dt over t, which we know is, well, we have a 1 over 4, so we'll have 1 over 4 ln absolute value of t plus c. Now, if we go back, remember that t here was equal to tangent of theta over 2. And recall when we did the trig substitution that x was equal to 4 tangent theta. Now, much like for the u substitution, or in this particular case, we need to basically solve for theta, and we've done this before with some trig substitution problems. So that means that theta here is arctangent, or tangent to the negative first of x over 4. And as we continue, here, we'll have 1 over 4. And remember, we solved for theta, so now that stuff has to go in there. So we'll have ln absolute value tangent. Again, well, actually, let me just write down what it would be. Plus c. Now we need to stick in theta, and remember, we already solved for that. Okay. So now this just becomes 1 over 4 ln absolute value, and we're going to still have our tangent, but on the inside we'll have arctan, or tan to the negative first of x over 4, and that's all divided by 2. And then you add a plus c to it, and that would actually be the answer. So your final answer here, it was dx over x times the square root of 16 plus x squared. And again, this was indefinite, so it'd be 1 over 4 ln absolute value tangent, and it looks like we'll have arctan, or tan to the negative first of x over 4, all divided by 2, and again plus c at the end. And that's your answer for that one. Alright, so maybe that one was a little bit more involved, but I think we did some relatively good work with it. So that's going to be your answer. Alright, so let me know if you got any questions, and I'll see you next time.